in the class. Okay. Okay. All right. So we can, do I do anything else? No, I don't think so. Let's just actually, yeah, okay. So people can still see my hand gesture. Okay. So hello, everyone. Welcome back to the Company 30 tutorial. So this is, technically speaking, tutorial 5, but really it's just the second tutorial I give in person. So this is really tutorial 5. So today we'll be doing some review for the midterm, which is Tuesday. Tuesday, yes. Okay. Yeah, so that's what we'll be doing today. So we'll be doing some review for the midterm. I was able to have a look at the midterm, and so this will be relevant to you. I didn't just come up with random, extremely difficult exercises that I can barely explain, just for the sake of that. These will be hopefully useful to your preparation. Okay, so that's what we'll be doing. So essentially, we're just going to be doing one sort of question, but in several different forms. Essentially, the exercise is just going to be to classify languages. And then we'll see that we can do sort of a bunch of different exercises just from there. So it will be to classify the following languages. Following languages as either, so the first option will of course be irregular, right? So in which case we'll have to, give an FA or a regular expression that accepts it or recognizes it. Or a language might be not regular, but it might be context-free, in which case we need to use the pumping lemma or closure properties or both to show that the language is not regular, and then either, right, so, first use the pumping lemma and or closure properties. Hello, hello. And then the second thing we'll need to do, right, to show that it's not regular, the second thing we'll need to do is either derive a context-free grammar or a PDA, which generates or accepts it, right? So that's the second class of options when we're given a language. That's going to be the second sort of possibility. And the last possibility is that it's not context-free, right? In which case we just need to use the pumping lemma for context-free languages, right? Here it's the pumping lemma for regular languages. Okay, and just a general guide, right? A general guiding principle when you do these kinds of questions is the first thing is when you're trying to determine whether something is regular or not regular, really all you need to sort of think of is there some sort of memory requirement that's needed, right? So does it seem like I need to have an arbitrary amount of sort of memory? Because for instance, for A and B and N, I have to remember an arbitrary number of A's and then check them with an arbitrary number of B's, right? So if it has to do with sort of remembering arbitrarily long sequences, or for an arbitrarily long amount of time, then the intuition is probably that it's not regular, right? Because DFAs are finite, right? So they can only encode finite amount of memory, right? And so that's sort of the hint to tell you whether something is regular or not regular. For whether something is context-free or not context-free, the hint I like to give folks is to just first think of whether or not you can use a stack to recognize the language. So can I use a stack to recognize it? Typically, it's easier to think about stacks rather than context-free grammars. Sometimes you'll be asked to generate a context, like to create a context-free grammar for a language, but in terms of determining whether or not it's context-free or not, typically it's easier to think of the stack. Okay. Okay. So we're going to start with this first language, so L1, and I'm going to write it down and then give you some time to actually do it. So I'm taking my phone out so I can start the timer. So the language that we'll be starting with is the language over the alphabet AB, where for every prefix of W, right? So every prefix of W has a difference between N, the number of A's and the number of B's, less than or equal to 1. Okay, so like to define this just a bit more, hopefully you sort of, based on assignment 2, you know what a prefix is, but if I have some string like A, B, A, B, A, then the prefixes of the string are, the empty string, A, B, A, B, A, B, A, B, and then the entire string, right? And so the condition in this language is whether in each of these prefixes, right, I have the condition that the difference between the number of A's and B's is at most 1. Okay, so try to determine what category, under which category this language is, and then try to prove your answer, right? But you don't have to prove the correctness of the construction you sort of create. Okay, so I'll give people 2 minutes. That seems like reasonable. 30 seconds is maybe not enough. So I'll give you 2 minutes, starting now. So for those on watching the recording, pause the video. I'll just wait 2 minutes. Hello. So we're doing an exercise. The exercise is given this language. Is it regular, not regular, context-free, or not context-free? And we have to prove that. So you have 1 minute and 6 seconds. Okay, a bit more accurate instead of me just counting to 120 in my head. Okay, so what do we think? Regular, not regular, context-free, not context-free? Any takers? No takers? It feels like you want to say something. Yes? Not regular, but context-free. So why do you think it's not regular?
It's not regular, like, have to remember, like, how many A's and how many B's, like, 24.
Mm-hmm.
So regular.
It feels it so yeah. Anyone else before we I feel like yeah. Just quickly. Yeah. Uh-huh. Yes. Which question in the assignment? Right. I see. Yeah. Yes, very wise. Okay. Good. Okay. So it seems like what you're pointing at is it's not regular because you have to sort of remember how many A's you've seen for sort of every single letter you're reading in the string, right? So this is a good intuition to start with, but let's actually consider this string that I wrote down. So I have A, B, A, B, A. So so imagine you're sort of starting at the start of the string, right? Then what do you care about when you're reading the string? Imagine you're the DFA, right? Imagine you're sort of a DFA or a PDA or whatever. You're a machine and you're sort of reading the string from left to right. Think of the easiest way for you to check whether the string was sort of following this necessary and sufficient condition, right? So, you see this first A, right? So that tells you that there's a surplus of one A, right, in the first prefix. Now you see this B, and you say, well, I had a surplus of one, now it goes back down to 0, right? Then I see this A, and I have a surplus of one, right? Then I see this B, and I have a surplus I go back to 0, right? Imagine here I had a B now. So this sort of 0 now that I had in terms of the count of number of A's and B's, now this goes back down to 1, right? So notice what has happened so far. So far, I've only really needed to remember 3 things, right? Whether the count so far between A's and B's has been 0, like the difference has been 0, whether it's been +1, or whether it's been -1, right? So what happens if I sort of exceed this count, right? If I exceed this count, here I'm at +1, right? And now I'm at +2. So so the sort of the crux of this is once I'm at +2, I don't care what's after the string, right? Because whatever is after the string, right? I already know that this prefix has 2 more B's than A's, right? So already this prefix does not respect this definition because this says every prefix of W has to have a difference of A's and B's less than or equal to 1. So as soon as I hit this sort of +2, then I can reject immediately, right? And it would be similar, right? It would be similar if I had something like A, B, A, right? So, I see this A, my sort of difference is +1. Now I go here, my difference goes back down to 0. Now I go here, it goes back up by 1. Now I read this A and it's +2, right? +2 means that I have a prefix, namely this one, that has 2 more A's than B's, right? So now I don't care whatever is after this. This is basically like me hitting a dead state and just rejecting whatever else is there, right? So that kind of tells you that I only have to remember really 3 things, whether the difference in number of A's and B's is 0, whether it's -1, or whether it's +1. Right, so only need to remember these 3 things. So if I read a letter where I go outside of this -1, so I go to -2, or I go outside this +1, I go to +2, then immediately I can go to a dead state and I don't have to sort of keep reading my string. Well, I have to keep reading my string, but my decision has already been made, right? So what would this look like? So this is the general intuition. Now to validate this intuition, let's try to make a DFA for this. So my start state is, of course, my start state, but imagine it actually encoded one of these 3 pieces of information. So the natural thing for the start state to encode is that the difference in A's and B's is 0, right? Because technically, my string, my DFA starts reading the string here, right before the string. And right before the string, I have no A's and no B's. So my difference is definitely 0, right? Then if I read an A, right? If I read an A, and I know, right? So here, my state is encoding the fact that I have the same number of A's and B's. So if I read an A, that just means I have one extra A, right? So if I have one extra A, then that tells me that I should go to a state that encodes a sort of +1, right? If instead I read a B, then I should go to a state that encodes a -1, right? And now if from either of these states, I read in this case an A or a B, that means that in this case, I sort of exceeded my sort of prefix condition by +1, right? So now I'm at +2. And I don't care what's after that. Like here, I'm essentially sort of dead, right? Dead state, I just reject anything, right? And if here I read a B, then my counter would sort of decrement to -2. And again, I would have a prefix. I have at least one prefix that negates this property here. So the reason why this has turned out to be regular is because the condition here is very, very strict, right? It says every prefix of W has this difference, right? Because it's so strict, I can just sort of go through letter by letter, read my string letter by letter, and I just need to update these three sort of memory states, okay? So there's a few things missing though. This isn't a DFA quite yet. So what happens, I mean, if I'm in the dead state, then I just keep rejecting, right? Now, if I'm here, right, if I'm in NA minus NB is equal to -1, and I read an A, then that means that, you know, my count was, I had one extra B that was making me -1. But now if I read an A, that means my -1 goes back up to 0. Because it was the B that was bringing me down. So now an A sort of balances that out, right? So this A balances this out, and I go back to my start state, which encodes NA minus NB is equal to 0. And it's the same logic, right? It's the same logic if I'm here. If I'm here, then the NA minus the NB is equal to +1 for the particular prefix that I'm at. Now, if I read an A that I have, then I have an excess of +2 and I just reject. But if I have a B, I have my +1 that's caused by this A. Now, if I read a B, then this +1 goes back down to 0, right? So then I have a B that goes back here. Okay, and this sort of gives you the logic of what I was sort of talking about here, where I was sort of increasing my window. I was sort of increasing this window of prefix. And I was only really saying, well, at this particular prefix window, am I in one of these three states, right? And then updating based on that. So there's, of course, a small problem with this DFA. What is the problem with this DFA? Yes, there's no final states, right? At this point, this is a very sophisticated, oh, that's bad. This is a very sophisticated machine that does this, which is not what we want. What we also don't want is for this laptop to die. So let us charge it. So what are going to be my final states in my machine? Is it going to be the start state and just the start state? Or is it going to be something else? Yeah. The three, yeah, very good, right? It's the three states other than the dead state, because each of those three states, they sort of satisfy one of these three conditions, right? And one of these three conditions respects the absolute value, right? Because NA minus NB less than or equal to 1 with an absolute value. When NA and NB are integers, there's only three possibilities, right? It's +1, it's 0, or it's -1, right? So very good. This, if I essentially make these three states final states, then that means that like these three together are essentially encapsulating this condition where, you know, if I have X here, X is a prefix. Right? Okay. And so that tells me that actually it was in fact regular. It seemed at first, I agree with you that it seemed not regular because it kind of looked like you had to remember the number of A's, the total number of A's, and then the total number of B's. But actually, the sort of crux is that you don't care about the total. You just care about the difference in sort of in plus or minus one. Okay. You had a question? No. Okay. Okay. Okay, great. So is this clear? Yes? Okay. Now, a question for you. If this is my DFA M, is M a, or really it should be the minimal DFA? It's another valid question that could be asked in the midterm, right? You've seen what minimal DFAs are. You see how to minimize them. So is this DFA minimal? Well, you could kind of look at it and be like, I think it's minimal. I think it's not minimal. Or you could just run the minimization algorithm and check, right? So the minimization algorithm, yeah, let's just do it. I have a quicker way of doing the minimization algorithm, but I think I should just show you what was shown in class. So remember what you do in the minimization algorithm is you make this table where it's sort of a 2D array where the entries correspond to states. Okay, and which of these states are accept states? This one, and this one. Okay, so then I make my table, and now I need to consider the distinguishability of states, right? So I only really remember when you're sort of doing the minimization algorithm, you don't actually care about the entire table. You only really just care about the lower part. I forget the matrix, the technical term for that, or the sort of top right part. And you don't care about the diagonal because, that's just checking whether a state is indistinguishable from itself. Well, of course, it's the same state, right? So all I really care about is sort of these sets of states, right? These pairs of states. Okay. And so the first step of my minimization algorithm after building the table, of course, is, well, I check which pairs of states are accept and non-accept, right? Because the states that are accept and non-accept, those are definitely distinguishable, right? They're sort of doing two different things. One is accepting, one is rejecting. And so I mark those with an X, right? So those are going to be which ones? Well, Q4 with all these three are distinguishable, right? Right? I mark these with X. So this tells me that there's not going to be like Q4 is not going to get grouped in with Q0, Q1, Q2. That actually tells me, oh, actually, you know what? I should have definitely told you what Q0, Q1, Q2 was. My bad. Say this is Q1. Right? So Q4, which is the sort of dead state, that's not going to get grouped in with any other state. That makes sense? Okay. So then that was the first step of the minimization algorithm. The second step of the minimization algorithm is checking this sort of distinguishability condition, right? So just to remind you, it's, you look at pairs of states. You look at pairs of states P and Q. And you say that P and Q are sort of distinguishable if there exists some letter such that so if this table, let's just call it the array A, if with that letter sigma, my table tells me that the pairs of states that I go to from P and Q are themselves distinguishable, then that tells me that the states themselves, right, are distinguishable. And this should be marked with an X, right? So you can just think of it as, if my final states and my non-final states are distinguishable, and one state, when it reads an A, it goes to a final state, and another state, when it reads an A, it goes to a non-final state, then those two also can't be indistinguishable because they do two different things. Like On an A, one goes to a final state, and on an A, the other one goes to a non-final state. So they're encoding different information. So let's check this one by one. What do we need to check here? So let's start with Q0 and Q2, right? So if I'm at Q0 and I'm at Q2, what happens if I read a B, right? If I read a B from Q2, I go to a non-accept state. But if I'm at Q0 and I read a B, I go to an accept state, right? So that tells me I'm distinguishable, right? And that tells me I should mark this with an X, okay? Then I do the same thing here for Q0 and Q1. If I'm at Q0 and Q1 and I read an A from Q1, I go to Q4. That's a non-accept state. But from Q0, if I read an A, I go to Q1. That's an accept state, right? So it's marked with an X. And so since it's marked with an X, since the sort of place, the pair of states I go to is marked with an X, then those two pairs I started with should also be marked with X's. So that will be X here. And then Q1 and Q2, right? Q1 and Q2. This one, if I read, let's see, an A, right? So if I read an A from Q2, I go to Q0. But if I read an A from Q1, I go to Q4. So again, that's distinguishable, right? So it looks like, right, I have X's on all my pairs of states. So that means I can't join any of those states together, right? So that means that yes, M is a minimal DFA. And in fact, I don't believe this was proved in class, but minimal DFAs are unique. So really, technically speaking, it should be the. Okay. So that's great, right? We're happy that it's minimal. Any questions about minimization? No? Okay. Question not about minimization. So to minimize? Regular expression. Where do you see regular expression? So you wanna find the regular expression for this? Yes, right?
Well, it's a regular language.
Yes, you
So
do.
we build an adaptive.
Yes.
Is that the only way to do that?
No, you can also build a regular expression. That was your question? You can also build a regular expression. Yes.
Okay.
Yes. Okay. I also kind of did a double take because the next question I was going to ask is, what is the regular expression for this language? So I also sort of thought you were reading my mind for a second. Yes. So what is the regular expression? For L1, right? Let's just remind ourselves what L1 is by copying this. Copy and then paste. Thank you very much. Okay, so the regular expression, right? So if you want to tell me what the regular expression is? Oh, yes. Yes. Is there a faster way to find the minimum here? Not that I'm aware of. No, this is the fastest way we have. Sorry. Yeah. I mean, there's heuristics, right? Like if you can check like, are all my states accept states, then the minimal DFA is size 1, right? Or all they are non-accept states, then that also has size 1. But other than heuristics, this is the best we got. Yeah. Sorry. It could be a research question. Work on it during your master's. Okay. What was I saying? Yes, regular expression. Thank you. Yeah. So there are essentially two ways of creating the regular expression for this language. One would be directly, and the other one would be through the DFA. Let's just look at the language and see whether we can come up with the regular expression directly. So, it says every prefix of W has to have this difference of NAs minus NBs being less than or equal to 1. So if I look at some string, right, let's look at a very, very long string. No, that's already not in my language. Yeah, let's stop there, right? So you could even tell that I was myself having trouble like writing down a string that was like sort of different enough. that tells you that there's probably a very simple pattern for the regular expression. So what do I notice here? I notice that if I'm not at the end of the string, right, and I have, you know, A's and then B's, I only have really two options, right? I have an A, and then right after, I have to have a B. I can't have right after an A, right, because that would give me sort of a +2. And if I have a B, then I can't have right after another B, because that would give me a -2. That would also be bad. So it looks like the only sort of consecutive, if I only think of the string in terms of pairs, the only pairs of strings I can have are AB or BA, right? So that's a good start. That tells me that the first part of the regular expression should be, you know, either it's AB or it's BA, right? Any number of times. And then, you know, this would be okay, but this would be okay if I was only considering strings of even length, right? But I can also consider strings of odd length, like this one, right? So the only time, right, the only time that I can have consecutive A's here or consecutive B's is if if sort of this second A is the last A, right? Because if it wasn't the last A, right, if there was a B here, then here I would have a +2, right? And that would be not good. Would I? No, sorry, I wouldn't. So if I had sort of two more A's here, right, then I would get a +2, right? So that tells me that when I finish, right, I can either just sort of stop with sort of interchanging ABs and BAs, or I can end with an A, because then I just have a +1 at the end, or I end with a B, then I have -1, or I just end with epsilon, right? So that tells me there's three options for the end. There's either I end with A, or with B, or with epsilon, right? And that's the regular expression. No, you cannot ignore it. So that's a good question. The question is, can you ignore this? No, because if you ignore that, then you would only have strings of odd length, right? Because then you would have pairs, and then one, right? So that's pairs, and then one. That's odd. Yeah. Okay. Good. Okay. Any other questions about? Yeah. Yes. Yes. Very acceptable. Very acceptable. Yes. Yes. You can just talk about it this way. Yes. The only way this wouldn't be acceptable is if it explicitly tells you to, from the DFA, to get a regular expression. And so that's great, because that's what I'm going to do next. So now I'm sort of, what is it, hammering this example to death by using it yet again to say, well, you know, suppose you didn't want to bother with like looking and thinking about how to derive the regular expression. How could you derive the regular expression from the DFA directly? Right? Because maybe, you know, it's totally fine to be like, oh, I don't know, or, you know, you're a bit, you know, exam level decisions are always okay. So it's fine if you're like, I don't want to think about it. I just want to run the algorithm. That's totally cool. So that's what I'm going to do now. I'm going to just sort of take this DFA and convert it directly to a regular expression. I'm not going to use the algorithm from class because I think that algorithm is very brutal. I'm going to use the one where yes, you can use that in the midterm. Yes. What was I going to say? I'm going to use the one where I just eliminate states. Okay. So remember that the state elimination algorithm, what it tries to get at, it tries to get at an FA that sort of looks like this, right? Where you have, you know, your start state and you have a single accept state, and the regular expression tells you directly how to get from the start state to the accept state, right? That's the state elimination algorithm. So how can I do this? Well, I can't directly start from this DFA. I have to sort of tweak it a little bit. The first thing I can do is I can already sort of delete this dead state, right? I can delete this dead state because once I'm at the dead state, there's no path for me to get back to the to a path of acceptance, right? So I can just delete this guy, right? Delete this guy and its edges, right? I don't have to think of, you know, what do I have to preserve from this graph by deleting the state Q4 because there's nothing worth preserving that actually goes to an accept state, right? So that's great. Now I have this DFA. Well, now it's no longer a DFA, it's just an FA. Now the other problem with this is I have 3 accept states, right? So what's a trick to say have n number of accept states and just have 1? Well, you just use epsilon transition, right? So you say, okay, these guys are no longer going to be accept states. I'm just going to have an epsilon transition to an accept state. Okay, great. So now the next thing is I need to start deleting states, right? So let's start by deleting the state Q2. So if I delete Q2, what do I need to account for? I need to account for the fact that Q2 allows from Q0 to read a B and then to go back reading an A to Q0. Right? So that's one thing it allows me to do. The other thing it allows me to do is it allows me to go directly to the state by reading a B and then epsilon. Right? So I have to account for this in my new graph. So I have Q0. I can stay at Q0 now by also reading BA. Now remember, this is a generalized transition diagram, so I can sort of use regular expressions. That's totally fine. And the other thing I need to do is I need to account for the fact that now, in addition to just reading epsilon, I can read a B to go to the accept state. B and then epsilon. Okay? And now I do this again, right? I do this again, deleting Q1, right? So you're never going to delete either the start state or the only accept state. You only want to delete all the intermediate states, right? So I delete this intermediate state Q1. So now what do I need to account for if I'm deleting Q1? I need to account for the fact that from Q0, I can go back to Q0 by reading an A and then a B. Or from Q0, I can go directly to this guy either by taking this path or by reading an A and then an epsilon. But then that's just an A, right? A epsilon is this A. So I need to add those 2 transitions. So here I have BA, but now I can also or use AB. And then to go to the accept state, I can either use B or epsilon, but now I can also use A. Okay? And now in this case, right, this sort of self loop on Q0, that can just become sort of, so this, if I sort of try to take off the self loop on Q0, this can just become BA or AB star, right? And then I either use B or epsilon or A to get the accept state. Okay, and then in this very nice case, right, from your experience on the assignment, it's not always the case that the regular expression you derive is the same one as the one from the converted DFA, right? In this one, it is, right? It's the exact same thing that we had started with when we had derived it directly here, right? So that's great. Regular expression, awesome. Any questions about this? No questions. Okay, excellent. So let's do another one. This is another language, so I'm starting a completely new question, right? Now that I've spent 30 minutes on the first question. This new question is asking you whether the following language over the alphabet AB is regular, not regular context-free, or not context-free. And in this case, the condition for the language is that the number of A's in W minus the number of B's in W is less than or equal to 1. You see what I did there? It's kind of it looks very similar, but it's not quite the same. Here, I don't care about every prefix. I care about the total string, right? The entire string. Okay? So I will again give you 2 minutes to try this. Let me start my time. Where is it? Oh, there it is. Okay. All right, starting now. Okay. So, what do we think? Any takers? Let's see, maybe let's try to see if anyone else is brave enough. I also just put on my glasses in case you think I look different. I think it's because of that. No takers? You want to give it a go?
I think it's context free.
Context free, but not regular. Why do you not think it's regular?
Because in the other one,
Yeah,
the fact that it was prefixes
yeah.
allowed us to actually not have to think of those strings.
Aha, very good.
Then we can
Yes.
just kind of like read them, but
Yes, yes, yes. Very good. Very
we
nice.
can't do this because it's the
Right. Yeah. Very good. Yeah, absolutely. Yeah. So here, right, I need to remember the number of A's for across the entire string, right? I have to remember it, right? Imagine you have you need a counter for a number of A's and a counter for a number of B's, and you have to wait. You have to wait until you get to the end of the string, and then you do the check, right? There's no other way of doing this, right? It's like if you want to compute the maximum in a list of numbers, you have to go through the list of numbers if you don't know anything about it, right? So it's the same principle. So yes, very good. It's not regular. It's not regular because, like we just said, you need to wait until the end of the string, and count the number of A's and B's. But now if you need to count the number of A's and B's, then you need sort of an arbitrary number of states, right? You need an infinite number of states really to do that, because the number of A's you could have is arbitrarily large, right? It could be any number of A's, right? And so that tells me it's not regular because there is that memory constraint now. And so what you'll actually notice is a very common thing. So notice that if you consider L2 and L1, right? Remember L1, that was the thing with all the prefixes have to have this difference. Then actually, L2 is a subset of L1, right? Because L1 is every prefix, right? The whole string is, of course, a prefix, right? But now, the reason why L2 is not regular, it's because you can imagine it's even harder, right? Like if you have some very large set, then it's very easy to distinguish whether or not something is in the set or not. But once you make the set much more specific, right, then it becomes much harder to have sort of a very simple rule to sort of distinguish between whether it is or isn't in the language. Yeah, you don't like this analogy?
Is it like L1 in L2?
No, right? Because you could have a string in L2, right? That has just A's and then just B's, but then the count goes down to sort of +1.
Yes.
But then the prefix, right? The number of prefix, like the first prefix might have like 3 A's and no B's. So then you have, oh, I see what you're saying. So then so you have a string in here, which is not in here.
If it has every prefix correct, then it is in L2.
Oh, yes, you're right. Oh, yes, you're right. Yes, you're right. Yes, you're right. Okay. Yes, very good. Yes, right? Because now, yes, because here you're forcing every single prefix, right? Yeah, thanks. You're forcing every single prefix to have a difference of number of A's and number of B's at most 1. Here it can be, well, you don't care about the exact prefixes, right? You just care that at the end of the string, then you have a difference that's at most 1, right? Yeah, okay, so then forget about that analogy I was giving you. But sometimes it turns out to be the case that you have a language which is much more specific than the language you had started with. And then it becomes harder to sort of distinguish between membership or not. Okay, so this language we're claiming is not regular. Now we need to, yeah? Yeah.
Can we consider like the prefix like part of the would have to go to that?
Right, you can't use the same reasoning. You can't use the same reasoning because what was going on here is as soon as I saw an A here, right, I would reject it because I would get like +2 in a prefix. But if I have, if I have +2, it might just be that I have AA and then BB, right? So then here I have a +2, but then my count goes back down to 0 after I read the entire string. So I really do, this just tells me I really have to wait until the end of the string. Like I can't just go prefix by prefix. Because when you're going prefix by prefix, it's not that you can go prefix by prefix and check the number and sort of check the entire string, right? It's, you have to go prefix by prefix and only check these 3 conditions, right? You're not checking every possible way that the number of A's and the number of B's can be at most 1 in the entire string, right? Yeah, so there's something to be said about necessary and sufficient conditions here, but based on the fact that I got this subset wrong, I won't tell you what it is because I think I might get it backwards. Okay. So does it kind of make sense though, why you have to wait until the end of the string? Yeah? Okay. Okay, good. So now we need to show that this is not regular. And so to do that, let's just use the pumping lemma, right? So the pumping lemma for regular languages. Okay. So remember, the way I like to do the pumping lemma for regular languages is I like to play a game where I'm the existential quantifier and I play against my opponent, who's the for all quantifier, right? So the for all quantifier is going to pick some natural number n, where that natural number is strictly greater than 0. Now what I need to do, right, what I need to do is I need to pick a string w that's in L2 and for which the length of w is greater or equal to p. Oh goodness, greater or equal to p. Okay? So how to write the common question, how do you pick w? You have to sort of think one step ahead. You have to think, if I pick some string, can I force my opponent to have some kind of decomposition where, given the decomposition, if I pump in a certain way, I'm going to be able to defeat the opponent. That's the general strategy. So in this case, there are many possible choices of W that you could pick. One possibility might be W is AP/BP, right? This is in L2. This is in L2. The number of A's and the number of B's are equal, so their difference is 0, right? And the length of W is 2p, which is definitely greater or equal to, right? Now, the reason why I picked AP is because now I know that in the sort of opponent's turn, when they go to decompose the string, right? When they go to decompose the string, they're going to have PAs and then PBs, right? And what the pumping lemma tells us is that the decomposition of W into XYZ, the XY has to be at most of length P, right? So that tells me that, I'll have X and I'll have Y, but Y is definitely not going to cross over to the B's, right? So Y is going to be, some number of A's, let's say KA's, and that number of A's is going to be at least 1 because the pumping lemma also tells us that the length of Y has to be at least 1, and it's going to be at most P because the pumping lemma tells us that XY has to be at most P. Okay, so now it looks like I'm in pretty good shape to sort of defeat the opponent, right? Because if I do something like I pump up by 1, then what will happen? So if I pick I is equal to 2, right? Then I'll get W2, which will be X, Y2Z, which will be X, YYZ, right? So X, YYZ is you're taking this Y and you're injecting an extra Y into the string, right? There's now an extra Y in my string W2. So now what does that mean? That means that I started with KAs from the Y, and now I add an extra KA, right? So now I have A, P plus K, B, P. And now I just have to check that the difference between the number of A's and the number of B's is strictly greater than one, right? Because then that would tell me that my string is not in L, right? So now I just have to check, right? So I have to check. I just have to check this. So I take my number of A's and I subtract my number of B's. Then that gives me P plus K minus P. And then this just gives me K because K is a positive integer. And now this is greater than one, strictly greater than one, right? No, right? It's not, right? K is not strictly greater than one because it's totally possible, right? It's totally possible that my opponent, right? Remember, it's my opponent that sets the K. My opponent chooses what K should be. So my opponent could be super sneaky and could be like, well, let's see what happens if they have K is equal to 1. And if K is equal to 1, then my whole strategy sort of breaks apart because now if this is just 1, then the difference between the number of A's and the number of B's is just 1. And now I don't have this conclusion. Okay, so what can I do then? What can I do to make my conclusion hold? Let's see if someone else, Ria, right? Okay. Pump more, yeah, sure, let's pump more. How much more? 3? 3, yeah, okay, let's see what happens with 3. I is equal to 3, so I get W3, then I get X, Y3, Z, then I inject 2 more Y's, right? I inject 2 more Y's into my string, so I get A, P plus 2K, right? So a very common error that students tend to make is they say, well, there's 3 here, so then it should be 3K, right? That's not true because one of the Y's is within the P, right? So that's why it's P plus 2K. So I have P plus 2K, and I have BP, right? And now, right, the difference between the number of A's and the number of B's, well, that's going to be, we can just drop the absolute value. So I get 2K, and K is at least 1, right? K is at least 1, so 2K is at least 2. So this is definitely, last time I checked, 2 is definitely strictly greater than 1. And so, yes, this is true that this is not in L for any of the choices, whoops, for any of the choices of my opponent here. Okay. Okay, so just before we move on, I'd just like to make a few comments about the pumping lemma in terms of common errors that students make. Okay. So one very common error that students tend to make is they set a particular P. Okay, so for example, sometimes students, say, well, I want P to be 17. P cannot be 17. You do not choose P. Your opponent chooses, right? Sometimes they say, P is even. You cannot make P be even. P is whatever your opponent wants it to be, right? If you want to make the length of your string even, then you have to do something like, so if you care about making your length of the string even, you have to do something like W is A 2P, something like this, right? Okay, so that's the first thing. The other thing is some students like to assume particular decompositions. You can also not do that, right? You can't say like, suppose X is epsilon and Y is A 32. You cannot do that. Y and X and Z can be anything the opponent wants. And the last thing is just related to the comment I just made. If you think about WI in terms of sort of like what the arbitrary pump is, if we consider like this example here, we're considering WI for this example here, then it's A power P plus I minus 1 times K and then BP. Okay, so there's this minus 1 because one of the K's is within the P. Okay, so these are common errors that hopefully now that I've written them down, you won't make. Okay, good. Is this clear so far? Yeah? Okay. All right. So that means it's not regular. Thank you. It's not regular, but we do think it's context free, right? So I agree. I also think it's context free. Now, how can we think about this in terms of using a stack, right? So maybe some of you watched the tutorial videos that I posted. In one of them, I do the PDA that accepts the number of A's is equal to the number of B's. Well, that's just the same as the number of A's minus the number of B's is equal to 0. So it's not that much of a stretch to think that, you know, if I open the window just a little bit, then it'll be handleable by a stack. And indeed it is, because imagine now my stack again implements the number of A's minus the number of B's, right? And imagine I sort of read, I just read some string here. Then I'm going to use sort of A's to indicate surpluses of sort of letters of A's, and B's to indicate sort of surpluses of B's. So here I read two A's. So what I want my stack to show is that it has two A's, because two like capital letter A's in my stack would mean that I have sort of a +2 difference. Then if I'm reading two B's, if I'm reading a B and I see an A, then I'll just pop it because I want my count to decrease. And then if I read another B, then I pop another A because I want my count to decrease again, right? So I'm just describing the logic of the PDA that's in the tutorial video. Now the only difference is now if I have an extra A here, so my surplus is by 1, then this should also be okay, right? So like if I just stopped here, then this is okay. But if I also have like a surplus of A's, a single surplus of A, or a single surplus of B, then both of these should be okay. And so I just have to account for that in my transition diagram. I just say, well, if I have an extra A, right? If I have an extra A, then I pop it, right? So I pop it without reading anything else because I assume that I'm at the end. So I just pop this, and then I check whether now my stack is empty, right? Because if I didn't read anything, if I stopped reading my string, and I pop this A at the top of my stack, and now my stack is empty, that means that at the end of my string, I only had a single A left. So that means I only had a surplus of 1. And it's the same thing if I do that for B, right? If I see that it was a B at the top of my stack, and I pop it at the end of my string, and now it's empty, then that means that I only had a single B at the end, and I just had sort of a surplus of 1 B. Yes. This thing? Oh, well, you know, suppose I had started with B, 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 like something like this, right? Right, then if I'd started with 3 B's, then in this case, I'm going to push B's to show that I'm sort of, B's refer to sort of -1, you can think of, right? And A's refer to +1, right? So here I'd have like 3 B's, so this would be -3 now. Then I read 2 A's, so I pop 2 B's. So now I have a single B, but now this is still okay, right? Because now if I'm at the end of the string, I just check, well, if I pop this final B, do I have an empty stack? If yes, then that's also should be accepted. Okay? Yeah. Wait. Yeah. Yeah. Okay. Right. Well, then that means that your machine guessed wrong, right? It guessed too early that it's at the end of the string, so it backtracks and it keeps sort of staying in that loop of reading A's and then reading A's and B's and pushing in popping. Yeah. So that's we're gonna see how that happens in the transition diagram. Yeah, but that's a good question. Yeah. Yes, mix of A's and B's allowed. It could be A, B, A, B, B, A, something like this. On this, not on the stack, not on the stack. It's always gonna, in my implementation, it's always going to be, if you have like a surplus of, let me just draw the transition diagram and then you'll see what happens. Okay. Okay. So what happens in the transition diagram, so this is my initial state. And so I'm gonna say if I read A's, right? There's three things that can happen. Right? Either I can have the dollar sign at the bottom, in which case I add an A, and I of course keep the dollar sign. Or I can have an A at the top, in which case if I'm reading an A, then I just add to my surplus, so I have two A's. And if instead I have a B at the top and I'm reading an A, then I have to sort of, in this case, make my stack more positive. So remove a B. Okay. Versus if I'm reading B's, then it's these three other cases where it's the same logic, right? If I'm at the dollar sign, if my stack is only empty and I'm reading a B, then I push a B. If it has a B at the top, then you add an extra B. And if it has an A, then I pop the A, right? Because I make it less positive, okay? And then normally, right, normally this would sort of account for the logic of, something like this, where you start at Q0, you read this A, so you have a dollar sign, then you push an A, then you read this B, so you pop the A, then you read two B's, so you push two B's. Then you read two A's, so then you pop these two B's, and then at the end, right, you have an empty stack. And if you have an empty stack, then you transition to the except state, right? Okay. Now this is for the number of A's is equal to the number of B's, right? Now I just have to make a slight modification for the difference being, at most one. Because now the difference could be, so now in this case, so this means that the number of A's minus the number of B's is 0. But now it could also be +1, and it could also be -1, right? So if it's +1, what that means is I want to allow the fact that I have an A at the top of my stack, right? But I don't want to read anything, right? So I only want to check this at the very end of the string. So if my machine checks early, right? My machine checks early, then it will go to this state, but then it will see that it has more to read, so it'll just backtrack. So, right, it's going to, at the end of the string, pop off this A, if there's an A at the top. And then now at this state, it's going to check whether the stack is empty. So to check whether the stack is empty, it's just going to say, well, do I have an empty stack? Right. And if I do, then I go to the except state. Okay. And then it's the same logic for if I have one extra B, right? If I have one extra B, if I have an extra B, then I want to pop it off, right? And I want to check that as a result of that pop, I only have an empty stack or a dollar sign, right? So then who asked me about backtracking early? You did, right? Yeah. So to your point, right? If, for instance, what's a good example, right? So if in this case, I push an A, then I pop it because I read a B, then I push two extra B's. So I have a B, and then I have two B's. Then I choose to use this transition, right? Right, so I say, okay, I think that I'm done my string right here. So I say, I'm going to pop this B, right? So I pop this B, and now I transition here. But now I check whether so here there would be one B left, right? But now I'm here, and I'm checking whether I have an empty stack, and I don't, right? So that's just like a failed computation, and that tells me I have to sort of backtrack, and I made a wrong decision, right? And I have to sort of choose something else. Does that make sense? No, it doesn't.
Oh, yeah.
Maybe?
Where's the back?
Oh, you can just think of it as an NFA, right? So NFAs, they try all the possible, right? They try all the possible choices, right? So you can imagine that it's like you get a tree with like a huge number of branches, right? So, if you're reading the first A, then there's many possibilities, right? Then at each of these, if you're reading a B, there's many possibilities. And then if one of these like fails, right? If I jam here, then it's just like a dead computation and I ignore it. The NPDA ignores it and it just says, well, what happens in my other computations, right? So it's backtracking intuitively, right? But per se, it's really doing everything and then seeing if one of them succeeds, right? If one of the computations, if one of the branches succeeds, then it's an accept, otherwise it's not. Yeah? Does this also make sense for your question, which I'm forgetting? My memory is bad these days. Yes. Does that make sense that it can intertwine? Yes? Okay. Yes, Angela. Yes, it also, yes, but you know, I'm not doing except by empty stack. I have 3 except states.
Like say, draw, like, make a PDA of accept by accept versus accept by continuously. I can draw if I. How do you draw one, you know, that? So this one, could it has to be?
I would say you should choose the type of PDA that's easiest to write down. But
Like, there's no graph for accept by accept.
right,
Is there like a graph where the PDA that accept?
a graph. What do you mean?
The topic graph for PDAs that accept.
For this language, yeah, they're equivalent, right? So there's a conversion algorithm from both of them. I just don't know off the top of my head. But I would say in general, if you're asked to design a PDA, just think of the acceptance condition that's easiest to work with. So in this case, this seems pretty intuitive to me. Yeah. Good? Yeah.
Can you like combine like states in this?
Combined states. Yeah, you mean like they would all go to this thing? Yeah, you could do that. Yeah, that would, yeah. Right, I mean, there's no reason why you should have these 3. You could say they all go to a single one, because you're always checking this condition. Yeah.
Is it possible to have like different elements in the stack?
Yeah. You mean elements as in?
Like, let's say you have this, like for any language.
Yeah.
And then in your stack, you can have like A, B, and.
Yeah, it's possible. It's possible to have like, it might be the case that this is what you want, right? Like for the palindrome example we did in the lecture, this is what you actually wanted, right? So yeah, it's possible to have, you don't always want to keep it sort of pure for one single element. Yeah. Good. Any other questions? No. So is this clear now? Yeah, okay, good. Okay, so I think what would also be relevant is, so great, we can make a PDA, which means context free. But it would also be nice if we could see what the context free grammar for it was. Okay. So let's make so this was the PDA. Now, what about the context free grammar? So I also made a video where I designed the context free grammar for the number of A's equals the number of B's. I can just quickly give you the intuition of it. So the context free grammars for the A's equaling the number of B's is this guy. Okay. And so the intuition is, you know, if you have a string like, right? The intuition is there are going to be substrings in your string where there's matching A's and B's, right? So you can think of, for instance, starting from S, you know that you can match this A with this B. And now it's all a matter of sort of matching and sort of redividing your string into smaller sort of substrings that have an equal number of A's and B's. Because if all the substrings in your string have an equal number of A's and B's, then the entire string has an equal number of A's and B's. Okay. So like here, I can say, well, S derives A and B, and then I get this variable S. Then using this thing, I can derive S, and then S, right? And then from these 3 S's, I can derive AB, and then AB, and AB, AB, right? Okay. And then there's a slight caveat, as in it's not always this nice, in which case you kind of have to use a graph that checks the difference between the number of A's and B's. And then the recursion actually happens on that graph. Okay? But if you want to know more about that, then you can just look at the video where I describe it. Okay? So this was for the number of A's and B's are equal, meaning that the number of A's minus the number of B's is equal to 0. So how can we now create the grammar that checks for the difference being at most 1, right? Well, the difference being at most 1, if you think about it in terms of sort of substrings and sort of recursion is, you might have, so there's 3 cases, right? If W is in L2, either the number of A's is equal to the number of B's, in which case you can just use this grammar, or you have 1 extra A, right? So if you have 1 extra A, then that means that your string, at some point in your string, you have this extra A, and to the left and to the right of the string, you have strings that are in sort of the number of A's is equal to the number of B's language, right? And you know how to generate the language for the number of A's is equal to the number of B's. So all you need to account for is the fact that you might have a sort of extra dangling A. Right? And then the same thing for if the number of B's was the sort of extra, right? So then you would have your string, and then at some point you have your extra B, and then to the left and to the right, you have strings that are of equal sort of number of A's and B's, right? So then I just have to implement this extra logic, right? So I can say, well, let's create a new start variable S prime. And S prime is going to say, well, either my string has, the same number of A's and B's, so it goes to S, where S is just going to be the rule that I wrote above. Or I can have this extra, I have to generate this extra A. And then to the left and to the right, I have the strings that should have an equal number of A's and B's. So then they should be generated by this grammar, because that's what it does. Or of course, I can also have an extra B, and then to the left and to the right, I could have the strings that are both of same number of A's and B's, right? And then this is going to be the context-free grammar. So this is G prime for L2. Okay, does this make sense? Yeah? Okay, many nods, good, great. Okay, now I'll leave this as an exercise because I'm running out of time in the lecture. So just a question for you, is this grammar ambiguous, right? So try this out. I'll leave it as an exercise. Okay. Because what I'd like to do, I'd like to speed run a conversion of this grammar into Chomsky normal form. Let's see if I can do it. So I'm going to take this grammar and I want to convert it into Chomsky normal form, right? Convert into CNF. Okay, let's take this grammar. We have to be smart here and use the copy and paste mechanism carefully. So I want to convert this grammar, right? So first step in my conversion to CNF, I have to remove epsilon transitions, right? So I want to remove epsilon production rules, not transitions, production rules. Okay. So if I remove the epsilon production rules, then what I need to do is I need to account for all of the places that I could have replaced. In this case, S gives me epsilon, right? So what are all the places? In this case, there's many. So, I could have replaced S with epsilon here. So I could have had AS. I could have also replaced this S with epsilon. So I could have had, SA. Or I could have replaced both with epsilon, and so I could have just had A. Okay. Then same logic for the SBS. So I could have had BS or SB or B. And then same logic for the S transition rule. I could have replaced this S with epsilon. So I could have done just S. And then, of course, I'm not going to consider replacing both by epsilon because then I would just add back the epsilon transition. And that would be pretty silly. So, so I'm not going to do that. Then I can replace this S with epsilon. So I get AB. And I can also replace this S with epsilon. So I can get BA. And so remember, in general, right, in general, if you had more than one epsilon production rule, then you'd have to do this for all of the variables. And it's also possible that you have something like, S gives you A. And then here I don't have any epsilon production rules, but I have A gives me epsilon, right? In which case, S can also derive epsilon. So I have to do the same process for the variable S as well. Okay, so that's something to remember. Okay. So I've removed all epsilon production rules. Great. Now I have to remove, what do I have to remove? No one knows? Unit productions, yes, very good, excellent. Remove unit productions. Good, I was very scared for a second. Well, I guess it's open, well, anyway. Never mind, I didn't say anything. Oh boy, yeah, that was not. Okay, so what are my epsilon, my unit production rules here? Oh, yes. So while there's one very easy one that I can immediately eliminate, there's this guy, right? So S gives me S. That's just useless to have. Let's just take that out. The other one that's a bit less easy to remove is this one, right? Because if I remove S prime gives me S, I have to add back to S prime all of these production rules, right? So let's do that here. Let's use purple. So I have to add SS, A, S, B, B, S, A, A, B, and then A. Okay, great. So now I've removed all unit productions. Awesome. Now the next step is what? The next step. Yes, non-generating production rules. So we do non-generating production rules first. So there was a mistake. I made a mistake in the tutorial videos, so that's why I'm mentioning this here. We remove non-generating production rules first. So all the production rules that don't actually give you any terminals. In this case, it looks like S can generate AD, so that's generating. And here it looks like S prime can generate A, so that's also generating. So in that case, I don't have to remove, right? But if I had, if I had, for instance, an extra rule like S prime gives you A S prime, and A, the production rules for A were like AA and BA, then this is non-generating, right? Because on the right-hand side, it only has non-generating variables, right? So then this is non-generating, so I have to remove these production rules, and I also have to remove this production rule, right? So that would be what would happen in non-generating. So I take this out, and I take this out. And then the last thing is reachability, so unreachables. So in this case, there are none. There are none here. For unreachables, I have to check whether from my start variable, so in this case, my new start variable is S prime, can I reach all the other variables? So again, in this case, very easy, right? Because I can only reach all of my other variables, because in this case, my only other variable is S, right? But an example of something that would be unreachable might be something, like I have S prime, S, all these rules, and then I have the variable B gives me S or S prime. Then, B can reach S prime and S, but it can't be reached by either S prime directly or through S. So then in that case, I would remove it. I would remove it from the grammar. Okay. Does this make sense? Yeah, okay, great. Okay, so great, that means I have a simplified, very heavy quotes, because not like simplified at all to me. I have my simplified grammar. Now I just have to do the extra variable trick to convert it to Chomsky normal form, right? Because remember, Chomsky normal form, I have the variable and the terminal, or the variable and then two variables, right? So the first thing I need to do is I need to add terminal production rules, so TA and TB. So TA derives A and TB derives B. And then I have to replace all of these where I see an A. Let's see. Okay, let's cheat and let's do this. Please don't do this in the, well, yeah, please don't do this in the midterm. Okay. Right, notice I'm of course not replacing A with TA, because then I would get a unit production. Okay, wow, there's a lot in here. Okay. All right. Right? Okay, good. But let me know if I'm making a mistake. Now the last thing I need to do is I just need to create like intermediate variables for production rules that have strictly more than two variables on the right hand side, right? So that's going to be, for instance, this guy. So this guy I replace with, let's do V1. V1 gives me STB. So I replace STB with V1. Is STB anywhere else? Yes, it's here. And then, so that's good. And then I replace STA with V2. Replace STA, V2. And then TAS and TBS. So V3 is TAS, and then V4 is TBS. Come on. Okay. And I'm good, right? So now this is in Chomsky normal form. Yeah? Okay, great. So now this is in Chomsky normal form. And now the great thing about this, now that it's in Chomsky normal form, is I can run the parsing algorithm, the CYKS algorithm. So I have -4 minutes, and so I don't have time to do that. But as another exercise, try to run the CYKS. Hopefully you know why it's CYKS and not just CYK. Run the CYKS algorithm on the string ABB, just for practice. Okay. So I wasn't able to do the last question. The last question was going to be this language a power n square. Those again going to be, is it regular, context free, not context free, and so on. So I'll just tell you the answer. The answer is this is not context free. In fact, whenever it has to do with like some complex operation on the power, it's typically not going to be context free. And in fact, so this is actually not, first of all, it's not regular. And it turns out that if you have a language which is a subset of just the singleton alphabet, and L is regular, then it turns out, there's a proof for this, that L is not regular, then L is also not context free. So that just means so that'll really, like, tangibly, that'll mean that the proofs for the pumping lemma will be the same, because they'll just be arguments about the number of A's and them not respecting, in this case, n squared. So, no comment. No comment, as in, you won't need to use it. Okay, good. Yeah, so just try this pumping lemma proof. Okay, and that's it for the midterm review. So good luck. And see you next Thursday, if I don't get sick again.